So let's say we have a simple 2 by 2 matrix. If you remember, we talked about this form of a matrix, AX equals B, where A is a matrix, X is equal to a vector, and B is a vector. So if we multiply the matrix by the vector, we will get the B vector. Now, this is also related to the inverse of a matrix, which we'll come back to momentarily. Okay, so let's say we have this matrix, square matrix with components 7, 3, 3, and -1. And we want to calculate the eigenvector for this square matrix. So this is our matrix A. Going to take an identity matrix and multiply it by the scalar lambda. So let's keep this as the given. Okay. And then we have the identity matrix, which we know is 1, 0, 0, 1. We will then multiply this by lambda. If you remember from the axioms of vectors, we can multiply a scalar by a vector. We can also multiply scalars with a matrix. And simply what this will do is we will substitute the ones with the lambdas. So this will be a variation of the identity matrix. We'll have lambda across the diagonal and 0 elsewhere. With this combination, we're going to subtract from the original matrix A this matrix that we have created, and we will represent this matrix as as lambda times I. Since I is used to represent the identity matrix, we're going to represent this matrix as lambda times I. So next thing we are going to do is subtract from the matrix A lambda times I. In other words, the difference of this matrix and the given matrix. Okay. This is that matrix, and this product is that matrix. Okay. The next thing we are going to do is, well, to subtract these two is to do the following. We're going to get a third matrix. We have 7 minus lambda, -1 minus lambda, and then of course the other numbers, which are 3 and 3. And this we will pass as argument the determinant function. So we will take this matrix, and then we will take the determinant of this matrix. And we've already seen how we can take the determinant of a matrix. It will be the product of these two numbers minus the product of these two numbers. And then we will get, let me just copy these. Now, if we multiply these numbers together, we will get the following expression. Okay, and then we solve, we do some algebra. So adding the -7 to -9, we get -16, but we also have to make sure to bring the terms with the higher order terms to the front. So lambda squared must come here to the front. Then we have -6 lambda, and then we get -16. Now here we have an unknown variable. That's the eigenvalue. So we need to find, you have to solve for lambda here. Of course, we will factor these two numbers to get, let me make some steps here. So this is, let's call this step 1. Subtract matrix A from lambda times I. Then we have step 2. Solve for lambda. So I'm going to copy this expression. We can factor these terms, so we will get lambda minus 8 and lambda plus 2. Of course, is equal to 0. And then so we will get that we will have two equations, lambda minus 8, lambda plus 2. If we move them to the other side of the equation, this will become lambda equals 8, lambda equals 2. So these are our two eigenvalues. So let's make this step 3. Let's make this step 3. Do excuse me for my handwriting. This is why I use LaTeX, to avoid having to correct myself continuously. Step 2 would be step 2 would be the determinant. Step 2 would be determinant of that. So the determinant of that, right? So, by the way, I will write this all down in LaTeX, so you don't have to look at this. It's just faster for me to do this by writing. Now what we can do is we can go back to the lambda times I matrix. So this one up here, we're going to plug in the values for lambda. Okay. As a matter of fact, let me copy this. I'm just going to copy this thing. This will be step 4. So for step 4, we have these two roots. We can use either one of them. Let's do 8 first. Although the solution will work for either one. Both of those will give you your eigenvector. So the step 4. So let's just bring this over here. Not the determinant, the difference of A and lambda times I. So that's this matrix. This is that matrix. So we will take one of those numbers, 8, and plug in for these values. So I'm gonna copy this and replace lambdas with 8. We have 3, 3. This is 3, and this is negative 9. Okay, let's do that. What do we do next? We represent this as a system of equations. So we can find x sub 1 and x sub 2. Where x sub 1 and x sub 2 are the values in the eigenvector. So step 5, find the eigenvectors. Eigenvector, single. We have the eigenvalues, we can now find the eigenvector. So to do this, we are going to create an augmented matrix. So I'm going to take this matrix, and we are going to have a square matrix. Excuse me, we're going to have a vector. 0, 0. essentially what this equation represents is the following. We have we want to find the eigenvector. So basically the vector that when we multiply by this matrix gives us that vector. And so the values of this vector are unknown, and we will say x sub 1 and x sub 2. X sub 1, x sub 2. So we have minus 1, x sub 1, plus 3, x sub 2 equals 0. Then we have in the second equation 3, x sub 1 plus negative 9, x sub 2 equals 0. And like we saw in the linear programming example, we need to solve these equations, or at least, eliminate one of them. Eliminate one of them. Let me show you what elimination means. So I'm going to, once again, we're going to augment the above matrix. If you remember what we said about augmenting matrices, so let me copy the whole thing. When you augment a matrix, what you do is you bring these two matrices together and then you separate them by some vertical line. This vertical line means there's an equation. So everything to the right side is an equation. Everything to the left side are, well, the variables. These are your variables, and these are the zeros of your equation. What we will then do is use the Gaussian elimination to find the x's. So I'm going to, for the time being, remove this the augmented part because they're all equal to 0. And so in order for us to eliminate this row, because once we eliminate the first row, the second row, then we have found, then we can solve for at least just one equation. So to do this, we are going to take row 1 multiplied by 3 times R1 and add that to row 2. And the result of this we will override, or we will put inside R2. Okay, so what we are doing is this operation. Multiply 3 times negative 1, so multiply 3. 3 we will apply to all the terms in this equation. So, and we actually remove the augmented matrix, so we don't need to worry about this anymore. This will become negative 3, negative 3. This will become positive 9. Add these two, well, I can't call them equations anymore. Let me bring back the 0. So they're equations. Now they're equations. If we add these terms together, what do we get? We get, well, everything becomes a 0. So the result of this addition, this will become the second row. The second row. In other words, after we perform this Gaussian, very simple Gaussian step, Gaussian elimination step, this matrix will become that matrix. And these become zeros. Now we can plug in these values into the equation. So remember, we have x sub 1 and x sub 2. And we want to know what these are. So to do that, we're going to say -1 x plus 3 x squared. And these are the values now. These are the values of x sub 1, x sub 2, because if we multiply this matrix with that vector, we will get these numbers. I need to set this to 0 and then solve for x sub 1 and x sub 2. So -1x will become, or rather what I can do is I can swap these. I can have 3 x sub 2 and then subtract -1x to bring this to the other side. So we will have 1x. And just to simplify the notation, that's just, and sorry, this will be positive 1x, positive 1x. And if we just lose the 1 because we don't put the constant there when it's 1, then x is just equal to 3 times x sub 2. That's x sub 1. And well, x sub 2, so here we have our vector. X sub 1 is equal to 3, right? If we swap the orders, we get 3 x2. Anyway, this is the correct eigenvector. Come back up here. We will have 3. So x sub 1, x sub 2. Now, of course, we need to do the vector matrix vector multiplication. In one sense, since RHS right hand side is 0, you can always divide by 3 and get back to the original. Yes. Now so this is now A. We have found the components for the eigenvector. Now now we need to multiply this. So we will multiply these and we will get times 3, then 3 times 1. Anyway, skipping the product and sum business, we will get this third vector, which is equal to 24 and 8. And what's interesting is that we can factor the scalar 8 from this matrix. So this is now B. So another way to represent this vector is to represent it like so. Is to go 8, the scalar multiplied by 3 times 1. And it turns out this was one of the values for the eigenvalue. So if you multiply this 8 by 3, we will get 24. Multiply 8 times 1, obviously, we'll get 8. All right. This is how you calculate the eigenvalues and how you find the eigenvalues and eigenvector for a 2x2. Very, I don't want to say tedious, but you have to first do the difference, find the difference of the identity matrix that is multiplied by lambda. Then you will get a third matrix. So then you have to take the determinant of that matrix. Once you take the determinant of that matrix, you will get this expression. And then you have to solve for lambda. And you will get 2 values, 2 eigenvalues.